Okay, so this is the lab practical lecture for Module 2 of Computational Chemistry for Experimentalists. What we're going to do today is work through computing the optimized geometry and vibrational frequencies of maleic acid and using that to predict the total energy and enthalpy of the molecule and use those to compute an enthalpy of isomerization. Now, I've already logged on to one of the remote computers in the Giga Lab, and I'm going to bring that desktop up now. Now you see I've logged in and I've got Gauss View up and running. The first thing that we're going to do is build a guess at the initial geometry of the maleic acid, which is a dicarboxylic acid. So we're going to go to File, New, Create a Molecule Group. Now I'm going to go to this R group tool and choose a vinyl group because that's going to be in the middle of the molecule. Now the maleic acid and the fumaric acid that we're modeling are both dicarboxylic acid, so I'm going to go back up to the R group tool, click on the carboxylic acid functional group, and put 1, 2 on this molecule. Now I've got a guess, an initial guess at the optimized geometry that this molecule might have in the gas phase. I can generate other initial guesses if I like. For example, I can take and modify the dihedral angle about this first carboxylic acid group. So maybe it looks like this, or maybe it looks like that. This particular molecule is probably going to have at least 3 different local minima geometry. One where both of the OH groups are on the same side of the molecule, and one where both of the OH groups are on different sides of the molecule. So 2 different local minimum geometries, actually 3 because they're going to be both with E versus Z configuration of the C double bond O versus the middle bond. What I would like you to do is I would like you for each molecule to compute all of the chemically relevant local minima that you think might be interesting, and then among those, take the lowest energy. If you really wanted to do a sophisticated calculation, you could do a statistical average over all of the conformations, but for our purposes, we don't need that. So what we have now is we have an initial guess at the geometry of the trans form of this dicarboxylic acid. In order to compute the total energy and the enthalpy, what we need to do is find a local minimum geometry as discussed in the lab handout, in the theory section. So I'm going to start, actually I'm going to modify this to what I think is a more reasonable geometry for the gas phase. I'm going to start by optimizing the geometry. So I'm going to go up and do a calculate and set up a new Gaussian calculation. My job type is going to be optimization. Later I'm going to do a vibrational frequency calculation. I'm going to use the default method, Hartree-Fock theory, 321G basis set. I'm going to use that throughout this lab, and we'll talk later about fixing that up. Now, we've discussed before about how some of the computers in some of the labs you might need to run some of these calculations from the command line. I'll have a different video on that, but right now this one should be set up to run properly, so I'm just going to submit this job. Mute this so we don't have to hear that beeping sound every 3 minutes. I'm going to save an input file. Now, you all could save this in a shared drive. I'm just going to use the documents folder on this desktop and move everything later. I've already saved this from working through it before, but we'll do it again. This is the maleic acid. Submit the file to Gaussian. And now it's going to do self-consistent field calculations, calculate a bunch of orbitals, and then it's going to do that over and over and over again at a bunch of different geometries, trying to walk downhill to a local minimum geometry. We'll just wait for that to finish. It should be no more than 30 seconds. Once we're done, we're going to take a closer look at this output file that's writing here because some of the information that we need is going to be in that output file. It's running, it's running, it's running. If we looked at that carefully, these total energies are going to be going down and down and down, becoming more and more negative. Now we're done. We're going to open the log file. right away we have a problem. Now I'm going to talk to you about how to fix that problem. So we're going to go to the File Explorer. This problem, you will see this online. You can find information about this online. But this problem, quote unquote, is an incompatibility between the version of Gauss View and the version of Gaussian 16. So I'm going to open maleic.log, the log file that I just wrote, and I'm going to open it in Notepad. Now you can see, and we're going to open these files again later in this discussion. So if you run into this problem, you scroll down, you scroll down, you scroll down. It's a bunch of information written out and wrote out, different geometries, different energies, going down and down and down in energy. And at the very end, we have that's strange. Failure reading molecule specification. Okay, so we're going to do this a slightly different way, because I don't see anything in this optimized parameter, anything in this log file that really should be a problem. I don't understand why that happened. But as you do these calculations, you find more and more different kinds of things that you have to sort out. So what we're going to do is we're going to prepare the formatted checkpoint file. So we're going to go into Windows PowerShell, and we're going to work from the command line. We're going to go into the Documents folder where I had all of these things, use the directory command, and I see that I have maleic.chk and maleic.log. So we're going to prepare a formatted checkpoint file. Take that binary file, maleic.chk, and convert it into a formatted checkpoint file. CCE G09 G16W form check.exe maleic.chk maleic.fchk. Now we have a formatted checkpoint file. It contains all the information that we need about this, and we can go to Gaussian formatted checkpoint files in Gauss View, open it, and now, finally, we have our optimized geometry. And what are some things we can say about this? First, at this level of theory, the molecule is predicted to be planar. Second, the carbon-oxygen bonds are now, the C double bond O double bond is now 1.20 angstroms. In our initial guess, it was 1.23. So things have optimized. The geometry has changed. The bond lengths have changed. The angles have changed. The next step is going to be to compute the vibrational frequencies, because this is what we need to get the 0-point vibrational energy and thermal vibrational energy components to the molecule enthalpy. Again, the details of that are discussed in the theory section. So for now, all we're going to do is take this molecule, take this optimized geometry, and compute a frequency using this same geometry. So I've changed this job type to frequency, and so you can see up here I'm using the same method as before. I'm going to use this same geometry that I optimized before, but I'm calculating a vibrational frequency. To keep things simple, I'm not going to compute the Raman activity. That'll save me a little bit of time. I'm going to submit this as a new input file. Submit it to Gaussian. And it's going to run, it's going to recompute the orbitals and compute second derivatives of the energy with respect to all of the Cartesian coordinates. And that's going to generate a new file. I'm going to try to open the log file. Again, that doesn't work. So I'm just going to go back to my PowerShell window and do all of this in the command line, and just you run formcheck.exe on my checkpoint file that I wrote there. Now I can open in Gauss View the vibrational frequencies. And I can go to my results section and I can look at things like that's going to take some work later. I can ignore that for now, but I have the same geometry. Now the last piece that I need to make sense of this, to get the isomerization energy, is going to be the total energy of this molecule. The total energy and the total enthalpy. Both of those pieces of information are in the log file. So I'm going to jump back into my documents folder where I'm saving all of these for now, and I'm going to go find maleic-freq.log. Open that in Notepad. This is my output, and I'm going to scroll down to a section on thermochemistry. So here I've done some calculations at room temperature, atomic pressure. So if this molecule was in the gas phase under standard conditions, what would I have? Well, I would have my total energy of the molecule would be up here in the section that says SCF done. Right here. So that is the total energy in Hartree atomic units of the molecule, where all of the nuclei are assumed to be perfectly classical and there's no vibrational degrees of freedom. That's in units of Hartree atomic units. It's relative to the zero of energy would be that all of the electrons and all of the nuclei are infinitely far apart. So this is an enormously large number on a chemical scale. When we look at an isomerization energy difference, we're going to take the difference between the maleic and fumaric acids, and the energy of maleic and fumaric acid difference is going to be maybe on the order of a few hundredths of a Hartree. So it's going to be changing down here in 731 versus maybe 450.735 Hartree. So these energy differences are small on this scale. But that's the total energy. That is U. What we want now is if the nuclei were perfectly classical. Our vibrational frequency calculation allows us to treat the vibrations of this molecule as quantum mechanical. And so after scrolling down, we get, in this thermochemistry section, a 0-point energy correction. So this sum of electronic and 0-point energies, that would be the real U that you would use if you wanted to get what's the delta U of these molecules at zero temperature. Sum of electronic and thermal enthalpies, this number is the delta H. And this number, sum of electronic and thermal free energies, is the delta G. Here the delta S is just computed for the vibrational and rotational degrees of freedom of the molecule. It's not great. I mean, it's a decent estimate in the gas phase. I wouldn't trust it too far, so we're going to focus on the delta H. And you can see that these numbers are all different. The 0-point energy is minus 450.642 Hartrees. The sum of electronic and thermal entropes is minus 450.634. So there's a difference, but this is the number that we want to use for computing delta H. That's what we need for maleic acid, for the trans conformer. Now what about the other conformer? This will be the last step that you need, and I'm just going to show you how to start. So we can take this optimized geometry, and we can use this modified dihedral tool to rotate about this double bond. This is going to be our second conformation. And now you can see here there's going to be a steric clash between these between these different groups, there's going to be something a little bit interesting here, which is that unlike the other molecule, unlike the trans case, in this cis case, if I move things around a little bit, I can generate what's probably going to be an intramolecular hydrogen bond should be available in this cis case. And you'll want to check by optimizing a conformation with this intramolecular hydrogen bond and a conformation without this intramolecular hydrogen bond. You'll want to check to see which of those conformations gives the lower enthalpy, gives the more stable molecule, because that's going to be representative of the conformations of the molecule in the gas phase. When you write your discussion, you'll want to discuss whether the fact that there's a hydrogen bond available in the cis conformation but not in the trans conformation, that's true in the gas phase. You'll want to discuss whether it's true in the solid phase and how that affects your gas phase versus solid phase results, and think critically about exactly what conformations you might need to best recover the solid phase results. But I will leave you to think about all of that yourself. So from this point, you would use this as an initial guess, re-optimize this geometry, recompute the frequencies, and that would give you your total energy and enthalpy of the fumaric acid, the cis conformer, and you could compare that to the maleic acid, the trans conformer, and get a delta U and a delta H, which will be ultimately what you want to compare to experiment. Now, that's all that I wanted to say about this lab. So go ahead, and I hope you enjoy it. Good luck.